presentations to all of the E3SM project. And we have two today. The first by Po Lun Ma, and I'll try and cut you off before 9:30, Po Lun, so we can go to our second talk by Andrew Bradley. And I think most of us, since there's so many online, should be on mute unless you want to talk. I can already hear a few people talking in the background. With this many people, you should be on mute and then unmute to ask questions. So I'll turn it over to you, Po Lun.
Okay, thank you, Mark. Today I'm going to talk about this new tuning results and some minor modifications I've made in the past year. And I want to thank the executive committee for giving me the opportunity to provide this update. And let me start from this slide that I am not going to the details of this slide, but just a reminder that EAM V1 is a very good model. And this slide is taken from Phil's slide to the advisory board committee. And what you can see here is that the EAM V1 model produces cold colors in most of the climate features that we usually look, and that means that this model is better than most of the CMIP 5 models. So this is actually a very good model. So how do we get there? I just draw this timeline to show the evolution of the EAM V1 configurations. So we have our V1 model all feature freeze in January of 2016, and then in February of 2016 we just had 1 month to tune the model to the top of atmosphere energy balance and a global mean, annual mean climate features to be reasonable. But there are known issues like aerosol and cloud precipitation distributions are not ideal. So what happens is that we then go to this research track that I check out the master code and then start doing some tests and simulations and tweaking. And at this time, I was tweaking the deep convections and cloud macrophysics, which is the club that treats the cloud macrophysics, shallow convection, and turbulent mixing. And in April, we created the second concept, which has a lot of improvements over the first configuration. And then in May, we create a third configuration, and in July, we create a fourth configuration. And then after the fourth configuration is created, the model is, EAM model is frozen, and except bug fixes and the tunings, we are not supposed to do any new features, and all the new developments should be considered as V2 features. But then we quickly found there's a bug that can affect the climate simulation, the cloud simulation. So we fixed that bug and then did some retuning to bring the top of atmosphere energy balance back to reasonable range. And that's the AV1C04P2 configuration. That's considered the official EAM V1 configuration. And in this configuration, we showed from this slide that this is a very good model, but we still notice several issues or biases. Of course, no global models are perfect. These are the biases that are outstanding for us, and they are clouds that we don't have enough coastal stratocumulus clouds, and this is a very common problem for all global models. And in the tropics, the cloud features are not good enough, and we have the Arctic clouds are also not good enough. And we don't have enough precipitation in the tropical Western Pacific, and we have a low bias over Amazon, and we have a high bias on high elevation. And the third issue is the TOA energy balance difference between present day and pre-industrial conditions. And this, I will talk about this in details later. So, but at this point, we have already, because we have all these deadlines to meet, and we create this great good model, but we haven't turned over every rock, and we haven't tried everything, so there are always rooms to improve. And so I check out this model version and started to do a lot of more research, and the purpose is to publish papers to document the V1 model and the V1 model tuning. And also, when I did this research, I found new things, and I have this personal desire to further improve the model. So I just did some more modifications, even though nobody tasked me to do these things. So a lot of these things are done in parallel with the main model development track. And then this is also important activity because because with V2 development timelines on the way, I want to figure out the development needs and opportunities for V2 and beyond. So the results out of this work might be useful. So I'm going to focus on these three issues: cloud, precipitation, and TOA energy balance difference. So the clouds, we have the list of issues here that we don't have enough coastal stratocumulus, we don't have enough clouds in the tropical Western Pacific, and liquid water path in high latitude seems too high. What I have done is to do a lot of retuning for the club. And first of all, this is the first time that I've tried to tune the skewness. And this is coached by Han Xiao at PNNL, Vince Lawson, and Chris Golas. And then I also did a lot of retuning for microphysics, and this is in consultation with a lot of experts on the team and from outside of the E3SM community. I also retuned the deep convection because during the time, in the past year, we heard a lot of issues in the couple simulation, and a lot of great diagnostics coming out of the couple simulation team. That's very helpful for me to understand what atmospheric features are not ideal. So I have targets to improve. And then lastly, I tried the gussiness parameterization over ocean. This is already in the code, so all I need to do is to change the name list parameter. So let me just demonstrate what the problem is. So this is the V1 model. This is observation from series EBAF, and this is the difference. I'm showing you the shortwave cloud forcing, and what you can see here is that the model doesn't have coastal stratocumulus clouds. So that's problem number one. And problem number two is that, so this is the zonal mean meridional distribution of liquid water path, and this is a V1 and this is a previous version, but they are pretty similar. So you can see that liquid water path in the Arctic is actually higher than that in the tropics, and I think this is unrealistic, despite the observational uncertainty, because we can't trust the satellite products in the Arctic too much, but so we don't have a good observational constraint for liquid water path in high latitudes in particular. But I just think this is not physically reasonable. So to deal with that, I am trying this. I found that skewness is actually very important in the cloud formulation to simulate clouds. So this is a figure taken from Chris' 2002 paper. From this region, this figure is showing the PDF of the vertical velocity, perturbation vertical velocity. And what you can see is that when you go down this way from top to bottom, then the skewness increases, and vertical velocity changes from symmetric to asymmetric, and you allow more strong updrafts. So that means in the low skewness regime, you are in the stratocumulus regime, and the high skewness regime, you allow more strong updrafts, and that's a shallow cumulus regime. So I'm plotting this the skewness from the V1 model. What you can see is that the spatial distribution makes sense, that you have low skewness along the coast, high skewness in the shallow cumulus regime. However, what you can see is that this area is probably not large enough, and the total the skewness is probably too high, which prevents low clouds from forming. So what I did was to tune the skewness by tuning this second momentum and the third momentum, because the ratio between them is the skewness. And then I also tuned the transition from low to high skewness, and then use the skewness dependency to tune this other mixing and the PDFs, so that this is a new skewness plot. You can see overall the skewness is reduced, which allows more low clouds to be formed. And the second important thing is that this low skewness area near the coast has been expanded. So this allows more coastal stratocumulus clouds to form. And so this is a new simulation, and this is the V1, this is the comparison. So you can see that I now have much more coastal stratocumulus clouds in almost every basin, or in every basin. So that's a big improvement. And the second thing is that I also tuned the microphysics and including the cloud phase and the burgeoning process, and to reduce the liquid path in the high latitudes. And now I think we have a much more reasonable liquid path distribution, which in the tropics we have high values, and in the high latitudes we have lower values. But this is not a whole story, because there's a new challenge here. So we know that stratocumulus clouds are highly susceptible to aerosols. So if we don't do anything else but just increase the stratocumulus clouds, that will greatly enhance this aerosol indirect forcing. And I actually have tried this, and so our V1 model's aerosol indirect forcing is 1.1 watts per square meter. But if we don't do anything else, just increase the stratocumulus clouds, the indirect forcing will be increased to 1.6 watts per square meter. So that will be very high. So that's clouds. And the second topic I'm going to discuss is precipitation. So we have this list of issues. We have low precipitation in the tropical Western Pacific. We have high precipitation in the Central Pacific. And these two undesirable features might be related to the weak ENSO signal in the couple simulation. This is just based on the couple simulation team's diagnostics in the last year. And the third item is the biased high precipitation at high elevation, for example, along the Andes. And the fourth one is we have low precipitation over Amazon. So these four issues are all very common in global models. And what I have done is that from a lot of discussions with people, and also from a lot of diagnostics from the couple simulation team, I retuned the deep convection scheme. And the second thing is that I use not only the gussiness effect over ocean, but I also enable the overland, turn it on for overland. And this is first inspired by Ruby's presentation in the All Hands meeting in June, where she showed one figure from, I think, Bill Lau's paper that shows that precipitation over Amazon is primarily from the local evaporation. And then Bryce Harrop did an offline study and showed that if we turn on the gussiness effect over land, it might also help the Amazon precipitation. And then Shibing and Phil and we also talked to the land group, and they also think this might worth a try. So after the meeting, I came back to Pian and Leo, and I couldn't help it, just try this, did a code modification and try this, and they did show some very interesting improvements. And I'll show in the next slide. So this is just a figure showing the biases I was talking about. And you can see that first we have low precipitation in the tropical Western Pacific, and we have the maximum precipitation in the Central Pacific. And these two features are not desirable for having ENSO signal, because ENSO actually depends on the difference of the relative strength of precipitation in the western and eastern side of the Pacific. And then because of this variation, then we can push the warm water eastward or westward. But if we have but our model currently produces maximum precipitation in the Central Pacific, which implies and doesn't have a lot of variability, and that also implies the water circulation might be wrong as well. And the third issue is that you can see along the Andes, there's this high precipitation, and same thing for along these Himalayas and the mountains here. And the last thing is that we have this low biasing over Amazon. And by turning on the gussness, which accounts for the subgrid wind, and then the new tunings for the deep convection and microphysics, that improves the precipitation. And you can see that we have increased the precipitation in the tropics. We've reduced the Central Pacific maximum precipitation. And we increased the Amazon precipitation, have reduced the precipitation bias along the Andes and these high elevation areas. And this is important for these precipitation improvements are also helpful for improving surface wind in the tropics. That because we have more precipitation in the tropical Western Pacific, now we have a westerly anomaly which prevents the cold tongue being pushed too far into the West Pacific. So that's an important feature. And then the second thing is that we also managed to reduce the surface wind stress in the Southern Ocean, which is always a bias and is common for a lot of global models. And the last thing I'm going to talk about is the system feedback and response. I think this is one very important but also very challenging part. So the list of issues here is that first, our top of atmosphere energy balance difference between present day and pre-industrial might be low. And the second thing is that the cloud feedback might be weak. The third thing is our aerosol indirect forcing is on the high side. What I have done is that I did a lot of sensitivity tests to find out parameters and processes that affect the aerosol indirect forcing and cloud feedback. And I retuned the model based on this sensitivity study. So just to give you a little bit of background, I've shown that we have created 5 configurations for the before the final V1 model is frozen. And the indirect forcing ranges from 3 watts per square meter to the lowest 1.1, which is the V1 model. However, the top of atmosphere energy balance, which according to series EPAF should be between should be about 0.8 watts per square meter, but our first 4 configurations don't really have enough warming, so that's actually pretty problematic. But our last one has a warming of 0.5 watts per square meter, and this is still much lower than the observational estimate. And the second thing is that our aerosol indirect forcing might be high. According to Beyond Stevens' estimate, it should be around 0.3 to 1 watt, and we are a little bit over that upper bound. And our cloud feedback is low. It's 0.25 watts per square meter per Kelvin compared to AR5's multi-model means of 0.6, ranging between -0.2 to 2 watts per square meter. And I did a lot of literature survey, and I found that, for example, the Keel paper showed that the equilibrium climate sensitivity from the couple simulation correlates very well with total adjusted forcing, and the total adjusted forcing correlates well with the aerosol forcing. So if we want to have a good delta rest home, we might need to adjust the aerosol indirect forcing, and right now our model is on the low side. But the aerosol indirect forcing estimate is really hard. So AR4 produces this estimate between half a watt to about 2.5 watt, and AR5 doesn't really reduces that uncertainty. where satellite estimates is between 0 to 1 watts per square meter. But of course, satellite has its limitation, and I wrote a paper to discuss that using the satellite simulator. And Bjorn Stevens published this paper using the Northern Hemisphere temperature trend as a constraint to say that to correctly simulate that temperature trend, the aerosol indirect forcing should be about 0.3 and 1 watts per square meter, and our model is 1.1, slightly over that range, and CAN 5 is 1.6, which is way over that range. So I did this sensitivity test, and I completed 27 sets of simulations, and I computed this aerosol indirect forcing and the cloud feedback, and I make this scatter plot, and this is the scatter plot. Each point shows one configuration where I change a process or parameter one at a time. And for global ocean, you can see that the process, when I change something that reduces aerosol indirect forcing, it also reduces cloud feedback. And so that's something to keep in mind. And the second thing I found interesting is that there's a very large regional variability. So in the Northern Pacific storm track, where present-day aerosol plays a role, these changes mostly affects aerosol indirect forcing, but have little effects on the cloud feedback. But for Southern Hemisphere storm track, this plot, and the changes mostly affects cloud feedback and doesn't change the aerosol indirect forcing because there's not much anthropogenic aerosols there. So Andrew Gettleman published a paper actually says that so aerosols might play a role in changing the cloud feedback processes. But I actually confirmed that aerosol does affect that, but it's not very large. It's only about 10%. So more analysis are needed to understand why it's showing this way. So I did a lot of this tests, and the results are summarized here. So I use these processes to then tune the model, and then so this is a newly tuned results, which I have an indirect forcing of 0.8 watts per square meter, so it's already within the range of the best estimates, and delta rest zone is much closer to the observational estimates as well. So the adjusted forcing is increased from 1.18 to 1.51 watts per square meter. So if we follow the Forster et al. Paper, which correlates equilibrium climate sensitivity to adjusted forcing by constraining aerosol indirect forcing and delta rest zone to agree with observations, we have decreased the implied climate sensitivity from 3.7 Kelvin to about 2.4 Kelvin. So this means that this model produces a much lower climate sensitivity when indirect forcing and the top of atmosphere energy balance differences are constrained. But more research, of course, is required to constrain and reduce this uncertainty. So in summary, I've improved the clouds through subgrid winds, skewness, and subgrid clouds microphysics. I've improved the precipitation through these processes. And I've improved the system response to aerosol and temperature perturbation through calibration at process level. And I think we need more observations and the LES results in various regimes to constrain this uncertainty of subgrid physics in order to simulate system feedbacks and response corrections. And I want to mention some computational aspects as well. So between March and August, we have, because this research track is not a high priority, so we have very slow progress. I have roughly about one simulated year per week. But after the leadership is aware of this issue, they've tried to make ENVO double the size of ENVO, and then Corey can become available, become very useful. So I've increased my the performance becomes 10 simulated year per day, so that's a much faster turnaround time. So I want to thank the leadership team and also the software engineering team and performance team for their help. And about 450 simulations are done and 600 standard diagnostics are produced and assessed. And the last important thing is that because I need to do this process level diagnostics, which requires high frequency and instantaneous output, and that takes about 400 terabytes disk space, and that's one issue. And the other issue is that performing diagnostics on this huge amount of data sets is challenging and requires parallel computing for processing those data. So this is just a list of all these new science-guided modifications inspired by or consulted with great minds in our on the team or outside of our community. And I've done all of this, and the green font indicates code modifications are needed because just some of the parameters are hardwired. And then lastly, there are some ongoing work, and this is the people who have offered their observations or LES results for me to use to evaluate our model, and some work being done in CMD VMCS to provide to explore better coupling, and there are some other issues as well. I'm not going to read it. So my goal right now, the first priority is to publish all these nice results, of course, to for the processes regulating cloud response to aerosols and temperature, and this paper 2 on improving precipitation over Amazon and Andes, and paper 3 on improving stratocumulus and stratocumulus to shallow cumulus transition using skewness, and other papers using observations or LES to constrain our model. So the last thing is to say how a near future possible upgrade is that we all these nice features can be integrated back to the main track, back to the master. So it will be a nice possible first configuration of the V2 model or a transition configuration. And the yellow font indicates what the things I have already started working on, the code and tuning integration. But to make a new configuration, we need to meet all these requirements, including code review, testing, and further evaluation, documentation, and finally the executive committee's approval, and we're not there yet. So that's my presentation, and thank you, and Merry Christmas.
Thank you, Po Lun. We'd clap if we weren't all on mute, I suppose. We have a couple minutes. I'm going to start the next one at 9:35, so we have a couple minutes for questions, 1 or 2 if there are any.
Hi, Po Lun, this is Xiao Cheng. Thank you for your effort to continue to improve our model. I have a question. If I remember correctly, the run you showed actually for the individual model problem are from different simulations. I know it's quite challenging actually when you improve one thing, like tuning one parameter that can improve the model overall, but it's great to know, at least we know how to reduce some of the outstanding problems we have. So my question is, have you found a single configuration that can improve all those problems, like, you know, the stratus, cumulus, and also precipitation, and also a aerosol indirect effect? So do you have any idea on this?
Yeah, so in October, Telecom, so that's very early results. So the simulations are labeled WW17, 50, and 51, and I think Chris said that he likes the 51 the most, but I was not satisfied with 51 either. So that's also intermediate results. But right now, after 2 months, I'm at the WW98, and the December 11th run is, I think, it's WW92. And that run is actually pretty good, and but there are just very minor things that I care, but probably if you don't look at the figures for hours, you probably won't see those issues. But what I'm saying is that we are much closer than 2 months ago, and so this configuration is finally coming together. And so this yellow thin code and tuning integration, the tuning integration actually means to put all these different features all together and then retune the model so that the overall climate is improved with all these improvements there as well. So that's what I'm doing, and I think we're close, and I'm confident that we can make the V2 deadline.
Okay, thank you.
Thanks again, Po Lun.